Assalamualaikum and a very good morning. Next, we are going to look at different types of antennas, starting from the very basic structure of dipole antenna, patch and microstrip antennas, to the latest trend for latest application using more complicated structure. Okay, the antenna can be classified based on four main criteria, which are the shape or geometries, whether it is wire antennas, aperture, printed, and so on. And in terms of gain, whether it is high gain, low or medium. In terms of the beam shape, okay, whether it is omnidirectional, pencil, or directional. And then depending on its bandwidth as well, whether it's wide or narrow bandwidth. Okay, these are sample of different types of antennas: the wire, reflector, aperture, lens, microstrip, dielectric array, and MEMS. Okay, from this slide onwards, I'll be sharing brief information about each type of antennas. So the first one is the wire antennas. So the basic structure is the dipole antenna and monopole antenna. So the difference between both monopole and dipole is monopole antenna above the ground plane, and the length is λ/4. So this is for monopole antenna. While for dipole antenna, it is combination of two monopole. Okay, and the total length for dipole antenna is λ/2 of the intended frequency. Okay, so the figures show some applications of dipole and monopole antenna. Okay, next is Yagi-Uda antenna. So we can usually see this in television aerial. And next is the helical antennas, usually used for the car aerial. And lastly, the loop antenna. Okay, next is microstrip antennas, so which is the patch antenna that consists of metallic patch each on a dielectric substrate. So you have this metallic patch that printed or placed on top of a substrate. So this is the substrate, which has a grounded metallic plane at the opposite side. So when we look at the bottom of this substrate, it will have a ground plane. Either it is a full ground plane or truncated design. Right, there are varieties of geometries for microstrip antennas. So, and modern integrated antennas often use multi-layer designs, okay, with a feed coupled to the radiator electromagnetically. Okay, so the figures shown the basic structure of microstrip antennas, but nowadays there will be more complicated design, as mentioned, multi-layers to cater multi-frequency bands and also multi-applications. Okay, next is the aperture antennas. I believe that you have seen this kind of antennas during your third year lab, okay, in which you have designed the horn antennas. So sample of or example of aperture antennas are the pyramidal horn, conical horn, and rectangular waveguide. These antennas usually designed within this frequency range, 1 to 20 gigahertz. And we can see that there's one narrow end and one opening end, in which the signal will be converted, the electrical signal will be converted into EM wave, and the EM wave will be radiated over free space to the end or to the receiver, and at the receiving end, the signal will be collected back into the opening end and will be converted back at the receiver. Next is the array antennas, which consists of multiple radiating elements. So it achieves unique radiation characteristic which cannot be obtained through a single element. Okay, when you look at the structure, this is the single element. So to start array antenna design, you will design the single element first, and then the same structure will be copied or be arranged in multiple rows and multiple columns. So you can achieve better performance, increase signal strength, and becomes more directive. Okay, sample of application using array antennas or smart antennas, MIMO, tracking antennas, and etc. Okay, another types of antenna is the reflector antenna. That usually used to concentrate the EM energy in focal point where the receiver or the feed is located. The advantage of reflector antenna is very high gain and directivity. Okay, some of the application includes radio telescope, satellite communication, and we can see this kind of antenna is used a lot in broadcasting. But the problem with reflector antenna, it is electrically large, okay, and then it's not easy to fabricate and difficult to make them mechanically robust. Okay, next is the lens antenna. Okay, plays similar role to reflector in which it can focus the EM wave. Okay, but lens antenna usually used at higher frequency, above 100 GHz, and the lens antenna can be classified according to their shape and the material they are made of. Okay, these are some examples of lens antennas, which are the convex, concave, and the application. One of the application is in cellular communication. Next is the DRE, Dielectric Resonator antenna, which is a ceramic-based material, and it is a non-metallic structure in nature. It offers high permittivity from 10 to 100. You may see a variety of shapes, hemispherical, cylindrical. Okay, the commonly used is the cylindrical and rectangular. And the resonant frequency of DRE antenna is determined by its dimension and dielectric constant. Okay, the advantage of this DRE antenna, it uses less metal, so in which metal may become lossy at high frequency. Okay, so DRE antenna may produce lower loss, more efficient than metal, especially at high frequency in microwave and millimeter wave frequency bands. Okay, next is the fractal antennas. Okay, fractal antennas is a self-similar design to maximize the effective length. Okay, it increases the parameter, so it can receive or transmit electromagnetic wave within a given total surface area or volume. Okay, the fractal antennas are compact, multi-band or wideband depending on the design, and usually used in cellular, telephone, and microwave communication. Okay, the fractal shrink its size, but it increases the bandwidth. Okay, without the use of any components such as inductors or capacitors, so it reduces or it is the design process. Okay, look at some applications of the fractal antennas. Okay, you can see this is the fractal antennas that use inside a mobile phone. Okay, in which it can have multi-band and wideband application. Right, the fractal antenna design process begins with the very simple structure of a square square shape, and then it is modified in terms of the width and the length, okay, until you achieve a certain dimension, and the structure is arranged to address certain or targeted characteristic or performance. Next is smart antennas, also known as adaptive array antennas, digital antennas, multiple antennas, and MIMO. It is in array configuration with smart signal processing algorithm used to identify spatial signal signatures, such as the direction of a variable, and use them to calculate beam-forming vectors for tracking and locating the antenna beam on the mobile or targeted areas. Right, it is more or less similar as the reconfigurable antennas, in which the antenna can be designed to focus on intended area or frequency. But for reconfigurable antenna, it is in single element, but the smart antenna is in array configuration. Okay, some application of smart antennas: DOE estimation, beamforming, interference nulling, constant modulus preservation, and etc. Okay, we can see some examples here in smart farming, in cellular communication, and various other applications. Okay, next is the active integrated antennas, which consist the passive radiating element, meaning the antenna, and the active circuit placed on the same substrate. Okay, we can see that antenna and the active components being placed on the same surface. Okay, for example, for mobile phone, we have the integrated antenna and also the active element on the same surface. The advantage of these types of antenna is compact, lightweight, low cost, low profile, minimum power consumption, and multiple functionality can be addressed or can be achieved. And some example of application in microwave and millimeter wave frequency bands. And something to ponder is low profile. I would like both of you to look at what's the meaning of low profile antenna. Okay, as we have seen variety of antennas in the previous slides, so but in this course we are going to focus only to 4 types of antennas, in which the theory and design will be discussed within weeks 6 to weeks 14. And these are the wire antenna, aperture, patch, and array antennas. Alright, in week 7, if I was not mistaken, there will be a representative from RF station, Senior Berhad, who will share a brief the introduction of CST software. Okay, although you have done some simulation using CST software earlier, so you may ask questions to them for further guidance. Okay, thank you.